Welcome to Understand the Math. In this video, I'll go over how to graph a basic and then a more complicated tangent function, and also walk through an example problem. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch this video. To learn how to graph the tangent function, we'll begin by writing tangent x in terms of sine and cosine. Tangent x is equal to sine x divided by cosine of x. Tangent x is going to be undefined when cosine x is equal to 0. If we look at our graph of cosine x, we can see that cosine x is equal to 0 at these points. We'll write down that cosine of x is equal to 0 at x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, etc. This tells us that tangent x is going to be undefined at x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, and then all the points after that. Tangent x is going to have a vertical asymptote at the points where it's undefined. We have one at pi over 2, and then we have one again at 3 pi over 2. Likewise, we have one at minus pi over 2, and then again at minus 3 pi over 2. And we'll label these. So we have 3 pi over 2, pi over 2, minus pi over 2, minus 3 pi over 2. And we have more to the left and to the right. We're just going to write these 4. Let's now draw our asymptotes. Our asymptotes are going to occur at pi over 2 plus n pi, where n is an integer. So that's 0, plus or minus 1, and all other points. To find the value of tangent x between the asymptotes, we need to look at the value of sine x and cosine x on the unit circle. The coordinate points on the unit circle are given by cosine x and sine x. So let's write that down. X is equal to cosine x and y is equal to sine x. Let's then remind ourselves that tangent x is equal to sine x divided by cosine x. We'll find the values of tangent x from minus pi over 2 at the bottom of our circle to pi over 2 at the top of our circle. I'll highlight the sine values in green and our cosine values in yellow. Those are our sine values, and now we'll highlight our cosine values. When theta is minus pi over 2, our sine value is -1 and our cosine value is 0. So that means that the value of our tangent function is going to be -1 over 0, which is an undefined negative number. So we'll write that as undefined and put a little minus. The value of tangent for our other coordinate points looks like this. Minus root 3, again taking the green, dividing it by the yellow. Minus 1 over root 3, 0, 1 over root 3, 1, root 3, and then lastly, again, an undefined, but this time it's an undefined positive number. I'll now fill in the points from pi over 2, going counterclockwise down to 3 pi over 2 or minus pi over 2. These points look like this. We have a minus root 3, minus 1, minus 1 over root 3, 0, 1 over root 3, 1, and then lastly root 3. We can see that every pi units, the value of tangent starts to repeat. The value of tangent is equal to 1 at pi over 4, and then when we go another pi units down to 5 pi over 4, our tangent is equal to 1 again, and that happens for all of the points. This tells us that the period of our tangent function is equal to pi. We'll summarize the values that we just found in this table. When x or theta is equal to minus pi over 2, our tangent is an undefined negative number. We'll write that as u minus. At minus pi over 3, we have minus root 3, and then the rest of the values look like this. Starting at minus pi over 2 and going to pi over 2, we can fill in the values of tangent by first plotting these values. And I'll indicate these with a little check mark. So we have a minus undefined number down there, and then minus 1, 0, 1, and then another number going up to infinity. We'll now connect the points to see what our graph looks like. Our graph repeats every pi units and looks like this. Our graph will then repeat indefinitely. Let's now quickly look at the general form of a tangent function so that we can graph functions that look like f of x is equal to 2 times tangent of 3x. Our general form looks like this. F of x is equal to a times tangent of b times x. Absolute value of a is called our stretching factor. If absolute value of a is greater than 1, then our graph is steeper. And if absolute value of a is less than 1, our graph is wider. And we'll see what that looks like when we do our example problem. B is our quantity related to the period. And P is equal to our period, which is equal to pi divided by absolute value of B. We can say that if B is greater than 1, we have a shorter period. And if B is less than 1, we're going to have a longer period. For tangent x, our vertical asymptotes occur at x is equal to pi over 2 plus n pi. So that tells us for the general tangent function, our vertical asymptotes are going to occur at pi over 2 absolute b plus n times pi over absolute b. We'll end this video by graphing the general tangent function f of x is equal to 2 tangent of 3x. We'll begin by comparing this to f of x is equal to a times tangent of b times x. and we'll make a note that A is equal to 2 and B is equal to 3. The absolute value of A is going to be equal to 2, and this is our stretching factor. It's greater than 1, so this tangent graph is going to get steeper quicker than the regular tangent graph. Our period is equal to pi divided by absolute value of B, which is pi over 3, and this is our period. Our vertical asymptotes are going to occur at x is equal to pi divided by 2 absolute B plus n pi divided by absolute B. And that's because tangent x has vertical asymptotes at pi over 2 plus n pi. So plugging in our B, this is going to give us asymptotes at pi over 6 plus n pi over 3. So let's make a note. That means our asymptotes are going to be at pi over 6, and then at pi over 6 plus pi over 3, which is pi over 2, and then it'll continue after that. Let's now write our asymptotes on our graph. Our first asymptote is pi over 6, and then our next one occurs at pi over 2. The one to the left of the origin occurs at minus pi over 6, and then the one to the left of that occurs at minus pi over 2. And then the asymptotes extend infinitely to the left and to the right. Let's now graph our function, keeping in mind that it's going to be steeper than our basic tangent function. And our graph repeats. You may want to go to desmos.com and graph the tangent function a times tangent of bx and see how the graph changes when the parameters a and b change. If you want to become more familiar with Desmos, you can go to my website and check out my blog post about it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.